Hello and welcome to the Science to Business workshop. My name is Kathleen Jimenez. Together with my colleague Julian Ebner, who will host the chat and poll today, I'm happy to host the session. Welcome everyone who's joining in. Today you'll hear 7 lightning talks from some of Austria's leading researchers in the field of computer science. Each sharing a quick insight into their work, giving you an overview of technological trends and perhaps ideas for potential projects with an academic partner. Even though Julian and I represent TU Wien, Austria's largest technical university, we are very excited to also be joined by researchers from the University of Vienna, one of the oldest and biggest university in Europe. Our goal for this session, to give you a glimpse into the latest academic breakthroughs. Each talk is short and designed to spark first ideas. If time permits, we will take one question after each speaker, but all speakers will share their contact details for follow-up. It is very fast-paced, so don't blink, you don't want to miss something. Use the chat to share your comments and questions and take part in our poll, which we will open now or in the following seconds. Perfect. The poll will be open during the whole session, and don't miss the results at the end. Maybe let's also test the chat. Send us a short hello in your native language or a greeting from the place you're currently joining us from. I'll just check the chat. It's the event support. Send us a hello or just, give us a sign that you're there. In the meantime, thank you all, and without further ado, I'm happy to introduce our first speaker today, Professor Uwe Zthun, Professor of Software Architecture at the University of Vienna. Please.
I think you have to unmute yourself still.
Yeah, I need to unmute myself. So you can see my screen, right? Okay. I like to give a brief overview of the research of the Software Architecture Research Group at University of Vienna. In general, we are working on software engineering topics, try to do cutting-edge research in architecture, design, and engineering. We have quite a track record of working together with other scientific partners and industry partners in over 35 industry projects. We have more than 250 publications in top-tier journals and conferences, and try generally to have collaborations with the leading European and Austrian industries. Our core topics are, as a software architecture group, of course, software architecture and design. Traditionally, here in the middle, you see distributed systems engineering. We work a lot on microservice, API, cloud, and edge computing. Nowadays, we work also a lot on different machine learning topics. Classically, we have applied in our core areas machine learning for software engineering. Nowadays, a lot of LLM-based topics, reinforcement learning, deep learning. But we are also very interested in software engineering for machine learning. Here, especially MLOps, so to support the production-ready machine learning systems, to build the whole architecture of a machine learning systems as opposed to just the machine learning solution. Generally, DevOps, CI/CD, MLOps, and LLM Ops are also important topics in our research. And in all these topic areas we are working in, we generally try to raise the quality, so quality assurance in all kinds of qualities that are interesting for a software designer or architect is a core topic of our research. At the bottom, you see 2 examples of qualities we were engaged with in recent projects. One is projects on security, privacy, and compliance. Another one is performance and resilience engineering projects, just to give 2 examples. To give you some more concrete ideas of some concrete projects, I have selected 2 of our recent projects. The first is MODIS. MODIS tries to address the challenge that there is still a lack of systematic methods for deploying machine learning models. In this case, we mainly deal with reinforcement learning models that our industry partner Siemens delivers for steering a shop floor in a factory. So it's about cyber physical systems, and as you know, Siemens has many different kinds of cyber physical systems. So these methods that we develop for MLOps could be potentially applied in many of the areas that Siemens actually works in. We developed LLM-based solution for local tools, static analysis tools, architecture guidance systems, and real-time quality monitoring for the MLOps pipelines in this project. Another project, quite a different area, but using similar kind of basic methods in our field, is AssureMOS. It was a European Union project and was on assurance and certification and secure multi-party open source software and services. So the idea was that we wanted to better ensure the security and continuous recertification in fast-paced open source development. Our focus here was on microservice design level security. The other partners, and you see there were quite a number of them, focused on all kinds of other levels, from code level to more security-oriented topics. And we wanted to shift the artifact-based security evaluation with scalable screening and risk analysis tools, and we provided those that are relevant for microservice design level checking and correction. Generally, we are looking here for industry and scientific partners to apply good cutting-edge research to real-world problems and create together innovative software solutions. If any of these topics is interesting to you, or you're interested in such collaborations, you can reach me at this email address, and we can discuss to have a meeting. You can also find more information about us at this URL. Thank you. Any questions?
Super, perfect. Thank you, Uwe Stoon. For everyone who joined us a little later, please post your questions in the chat. I received one directly that, can your research be customized or applied to specific domains, such as healthcare or other?
Yeah, in general, our research is domain agnostic, so we applied it in quite a number of different domains. The example in the MODIS project, for instance, was a CPS system, but we also have a lot of things in business systems and all other kinds of systems. So that's really quite open.
Super, perfect. Thank you again, Professor Uwe Stoon from the University of Vienna. Thank you also for being right on time.
Okay, thanks.
Next up, I welcome Jürgen Zito, Associate Professor for Software Engineering at TU Wien. While he's sharing his screen, please use the chat, use Q&A to post your questions in the meantime, or comments.
All right. Well, good morning from my side. I will also try to keep it brief. I know Kathleen and I talked yesterday that there's not a lot of time and there's a lot to talk about. I want to talk about accelerating productivity in software engineering with AI. What I mean by that, at the center of our research is always a software engineer, or more generally, someone who works with computation, a data scientist, an infrastructure engineer, and oftentimes they work with code. So they produce some kind of source code to achieve their goals. That usually goes to some sort of continuous integration and eventually deployment. And along this path of engineering, software engineering, we want to make software engineers, data scientists more productive. And we usually do that by collecting data along the way. So either at deployment time, when people use the software, we can have runtime traces through observation. We can trace something about the build artifacts or test results while in continuous integration, or even at the source code level, how the software evolves over time. So this is the pipeline that we use to enhance the productivity of people. And when I say we, I mean the IPA lab here at TU Wien, which is the lab I'm leading. And usually we do two things. One thing we do is empirical understanding. We try to understand what the problems are through rigorous empirical methods, both quantitative and qualitative. And on the other hand, we try to build systems. So in the end, we want to be able to intervene into the process to make it more productive. What I want to show you in the next couple of minutes is 3 highlights recently that we worked with industry with. One is in AI for security testing, debugging machine learning models, and agents for automated bug fixing. So a very recent project with one of my PhD students is where we use large language models and an agent-based system, as you can see on the left side, to produce a series of commands to a system to, in essence, hack it for the purpose of securing it. And on the right-hand side, you can see a bunch of results where we indeed were able to hack these systems and are able to show the vulnerabilities of that system. So this is something that has been very successful here. We're looking for people to actually try it out with in an industry context. And these are not like, let's say, toy systems. As you can see here, these are actual systems where we produce a lot of traces to produce a attack graph over the system. So this is an interesting project, I think, that has some industry relevance. Another one is a recent project we had with Meta or Facebook back then, which was how can we explain when a machine learning model that you may have in production has gone wrong. And the challenges here are in the high dimensionality of these input spaces that you have in machine learning models. The models that you're deploying are usually opaque. You don't know what they're doing. And actually testing what's going on is not feasible manually because there are a lot of combinations you may have to test. So in this example, the issue is that overall, you may think that the accuracy of your model is pretty good. But if you drill it down to the actual subpopulations of your model, you may be able to see that your model doesn't do well on certain populations. So this has to do with also fairness and bias in your models. So if you're thinking that maybe your model may be going wrong at certain places, this is an approach we built and deployed within Facebook together to identify these things. And the last project that I want to briefly show is a very recent paper that we brought out with Google. This just happened like a couple of months ago, where the problem was, can we fix bugs automatically? So if someone has reported a bug in your system and there's a text from your bug repository, the goal of this project was to produce a patch, namely a change to your system that fixes that bug. And how are we able to do this? Well, we teach large language models a certain set of commands as if a software engineer would use them. And then we let the agent, in this case, over a certain number of steps, try to fix that bug automatically. Okay. So this was a super exciting project, and this was a very tight collaboration with Google, and we just published a paper on this. Okay, so this is just a sample of what we can do. In general, we're interested in collaborations where you have developer productivity in mind, you have a software engineering process that you want to improve, and we're happy to work together in different contexts. So please reach out either on the chat or by email, and I'd be happy to talk more.
Super. Thank you very much, Jürgen. Yes, please. Are there any questions in the chat? If you are shy, you can also contact the researchers directly. There's a possibility in the chat to just write your questions directly to the researchers. Get in touch with us. Thank you, Jürgen, also for the invite. Next up, I'm happy to introduce again a researcher from the University of Vienna, Sebastian Schrittwiese, senior scientist at the University of Vienna.
Sebastian, we don't hear you yet. Sorry.
Yeah, sorry. Thank you for the introduction. I'm from the Security and Privacy Research Group at the University of Vienna, and we research on a broad spectrum of security and privacy topics, so ranging from software security over industrial security to security awareness topics. And today I want to introduce Awareness 365, an ongoing project on phishing awareness. So a recent study showed in 2023 that over 40% of all attacks on computer systems start with a simple email. So making phishing the most common initial attack vector in attacks on computer systems. And on the other hand, companies do invest a lot of money and effort and time in security awareness, at least for the last 2 decades. And so the big question is, why is social engineering, such as phishing, still highly effective for attackers? And how can we do better? And Daniel Kahneman is a world-famous psychologist, proposed an explanation in 2011 in his popular science book. It's called Thinking Fast and Slow. And his basic concept is that he describes 2 different ways the brain forms thoughts. So we have a system 1, it's fast, automatic, frequent, emotional, stereotypic, unconscious. So things we can do in system 1 is, for example, determine that an object is in greater distance as another one, or localize the source of a specific sound, solve simple things like 2 plus 2. And on the other hand, system 2 is slow, effortful, infrequent, logical, conscious. So things we can do there is, for example, we can direct the attention towards someone at a loud party, or try to recognize a sound, solve something like 70 multiplied by 25 or so. And traditional security awareness, such as a half-day workshop on phishing prevention, for example, trains system 2. So we tell users to not click on a link in an email if it looks suspicious or so. But the problem is, if a phishing mail arrives, it triggers system 1. So we react quickly, click on the link, do it basically automatically, because all of us get so many emails a day. We need to train system 1. And this can't be educated, it has to be conditioned. So we need something that exposes it to frequent, realistic exposure to build up some pattern recognition scheme. It's like fire drills. So repetition makes people then react correctly to a real fire. And in 2020, we started working together with a psychologist to research the optimal strategy to train user system 1 in the context of phishing, to make them resilient against social engineering attacks, and in particular phishing. And now we are working on Awareness 365. It's a system that generates tailored simulated phishing emails to train this pattern recognition in system 1. Also give on-spot feedback in system 2, so explain what happened if someone clicks. And it's more or less integrated directly into the daily flow of the user. So instead of what typical phishing simulations do, sending one phishing email, test email to everyone in a company, we do it infrequently. Everyone receives other emails created by LLMs. And what our system is based on is, for example, basic principles of phishing emails. So, for example, trust or urgency, fear, all these different principles trigger system 1 of users differently in different ways, and we train all of them on their own separately. We also have specific themes with specially crafted prompts for a language model that then is able to generate these emails. It's also possible that a user replies to an email, might be suspicious, and user could ask, and the LLM will craft an additional email, will reply back, will answer maybe the questions of the user to simulate what a real attacker would also do in practice. yeah, and the system is also able to customize messages to a user by collecting information about them, so the department they're working in, where they live, their hobbies, and incorporate everything they know about them in their messages. Yeah, we're currently evaluating the system together with approximately 2,000 test users in about 40 companies, and further refining the concepts, the templates, the integration of the LLM, and so on. So if you're interested in applied research projects in the field of security awareness, I would be more than happy to talk about opportunities. And also, if you're interested in helping refining awareness with 365, awaiting it, just drop me an email and we can add you to the test companies, and so that you get a feedback what we can do with this security awareness training. Thanks for your attention.
Thank you, Sebastian, and also thank you for the invite. I for sure know that our IT department at TU Wien sends out phishing mails regularly, so this might actually be interesting. But yeah, we don't have time to take questions. Maybe you received some in your direct chat. Just check them, Sebastian. But we need to move on to the next presentation, and I welcome as a next speaker Daniel Müller-Gritschneder, full professor of embedded computing systems at TU Wien.
Good morning from my side. Okay, welcome. So we are now changing a little bit the topic. So I'm more working in the embedded domain, and I want to kind of pitch a little bit the ideas of bringing ML into smaller systems. So what we see is this is kind of a plot that this is a 10 years span, that actually a number of sensors is rising. So you can barely see in a 10-year period, it's barely doubling in a lot of fields how many sensors we are deploying into the field. And what we are working on is how can we make these devices smart devices? And the answer is called tiny machine learning. This is a now very fast growing market. And I want to today kind of give you a little bit the idea what TinyML is, how it relates to Edge AI, and how you can use it in your systems. So if you look here on the right side, in a classical system, you would have a lot of sensors deployed. These sensors stream the data to some edge or mobile device, and then they're kind of aggregated and further streamed into the cloud, and the intelligence sits then in the cloud, and you run your intelligence there. If you move more to an edge AI system, you would move this intelligence to your edge device, which would be like a mobile device or a PC or an edge GPU. And then you would be nearer where the sensor, where the data is produced. And to go extreme, you would even actually move that further. You move it directly on the sensor devices. And this is what is called a TinyML. And this has a lot of advantages. Of course, you need much less bandwidth. You can react much faster, so latency is reduced. Privacy is enhanced because the data is not moved to the cloud. Usually you can save a lot of energy because streaming this data is quite expensive. And you give all these devices a certain level of autonomy. Well, it's not an easy task to do because especially then on this extreme edge or TinyML, the devices are very constrained. So it's actually quite difficult to develop this system, and it kind of requires a skill set which puts together embedded programming and machine learning in order to make this happen. I'll give you just a few examples here to show how small this can get. These are 3 examples. So one is like a small camera you can basically swallow, and it will do a diagnosis inside your body, right? So it basically travels to your body, and then there's a small vision system inside there. It finds out at which location it is, then to kind of increase the frame rate when it becomes kind of the region of interest. On the right side, it's not so easy to see. This is actually a safety vest, which actually detects whether there was an accident. So a construction worker having like a small battery-powered sensor. If there's something happening to him, this vest would report it. On the lower side, you can see something which is coming more from the automotive domain. This is a gesture recognition. Basically, it's used for touchless control. And actually, this was a system we also set up, and you can see basically how tiny it is. So the sensor microcontroller is basically in the range, of kilobytes of memory instead of, gigabyte. But still, you can use data-driven approaches, neural networks to actually make a pretty nice pattern recognition on this device. So basically, the application areas are kind of endless, right? Just like taking all these sensors we have available. And from our side, so from my group, we have been working quite a lot in this field. So we really cover, since it's very small devices, we can really cover the whole stack from the algorithms down to the hardware, even looking also into fault tolerance to make this tiny application happening. We have a lot of industrial collaboration already going on. So we're working on a motor control application with Infineon in Munich. So I was in Munich before I switched to Vienna for a long time. In Austria, I have a collaboration, or had a collaboration with a company called USPAD, and together with another Austrian company, Spark Systems, we kind of build a smart ultrasound sensor for liquids. And more on the bigger domain, like Edge AI, I'm also working a little bit on vision systems. We do model compression and neural architecture search to make these systems run better on specialized hardware, where I'm working with BMW in automotive. And we actually also were successful in a proposal in the last Edge AI call from the FFG for a light project. And there will be a new project starting, which is called Domino. And there we will look into vision for rail and industry. And from my background, also I'm a computer architect, so we also bring it really down to the hardware. So if you're really also into like designing your own chips, we also working on specializing the chips to really run these workloads faster and also safely. All right, this was very quick walkthrough. So if you're interested in this field, if you want to bring ML or AI to your embedded applications, I'm always happy to learn about this, always looking forward to collaboration. And it's really not that hard, I would say. So bringing companies up to do that is not very hard. There's a little bit of a knowledge gap for a lot of embedded developers, but it actually doesn't take them a lot to understand, how they can use this AI kind of systems within their embedded applications. Okay, thank you very much.
Super, thank you, Daniel, and thank you also for motivating the companies and inspiring them to take a chance and start a collaboration, even though there is maybe a knowledge gap. Next up, I welcome Clemens Heitzinger, co-director of TU Wien's Center for Artificial Intelligence and Machine Learning, KAIML. Please share your presentations, share your slides. In the meantime, dear guests, participate in our poll that you can find in the lower bar and the chat. Okay, the slides are here. Here you go, Clemens. The floor is yours.
Hi, good morning, everybody. So another change of subject. I will talk about some applications of machine learning or reinforcement learning in particular. So basically what we do is lots of optimal control nowadays. There are a number of examples that I will touch on. For today, I chose two examples in particular. Both are medical examples. So the first one is the early detection of solid tumors from blood samples, with the obvious implications for oncology. And the second example is decision support in intensive care units, where we have also used machine learning in order to develop decision support systems. All right, what does optimal control mean? Well, we have some system that we try to control. So that could be some expensive machinery. It could be the patient trying to make them healthy again. So that's the environment that you can see here on the top, and we make some observations. Those observations we call the state. And whenever the system behaves as you would like it to, then we obtain a reward, or the agent obtains a reward. And our goal is to maximize the reward. For example, if we can save money by operating our machinery in a better way, right? These savings would be the reward. And the goal of the agent is to learn policies that give us that give us actions that really make the system behave as we like it to. So that's a very general approach. It has been all over the media when Google DeepMind solved chess, Go, and various computer games. And we are mostly interested in safety critical applications. So I'll skip over these slides here, and I'll talk a bit about a safety critical application in intensive care. So what we do is we collect data sets of intensive care patients. So those are followed for 2 or 3 days very precisely. There are lots of data points that are collected, typically every 4 hours. And based on this historic data, we calculate optimal treatment policies. Why intensive care? The data availability is very good in intensive care, and sepsis is also the most common cause of death in hospitals and in intensive care units, so that's a logical starting point. So we developed a quite sophisticated setup here, including data cleaning, imputation, most importantly, reinforcement learning, and maybe half of the time is spent on really making sure that whatever we learn, the policies that we learn are optimal. So we have mathematical theorems that show us that we converge to optimal solutions, and we have also various independent ways to show that whatever we calculate actually makes sense and is a good solution. Typically, what we try to achieve is superhuman performance, and so far, let's knock on wood, in all the applications that we have looked into, we could achieve this. In this particular case, we compare our policies to what clinicians do, what we have in the historic data, and we can say with very good confidence that we reach the human level and we even surpass it slightly.
Dear
In
Clemens,
addition,
I'm sorry to interrupt. I know it's hard to break down the whole work in 4 minutes, but you have 1 minute left. If you maybe
that's perfectly fine. Yeah,
Yeah?
1 minute
Okay.
is enough. So what we also do is we can quantify risk in many applications. That's important. So we, in each state of the machine, we can, or the patient, we can tell you, is this a risky state, or are we doing well? Is this a state that the human should look into if we have a decision support system? Solid tumors, we also achieved very good results. So this is mainly a supervised learning application where we had patient data from a couple hundred patients, and we can predict with good confidence if they are close to developing a tumor or not, that can be detected using classical methods. All right, further applications are industrial applications. So you see here a couple of research projects, FFG, also FWF projects. I have not touched on the industrial applications, but we are interested in those where money is at stake, and those are usually safety critical as well. I would say we have lots of expertise in machine learning, in stochastic optimal control, aka reinforcement learning, in mathematical modeling and simulation, and in partial differential equations. And I would be interested in talking to companies that work on medical applications, or any other companies that are looking for serious expertise in AI machine learning optimization and or mathematical modeling. And I'm also looking for investors in software tools in medicine in order to develop and market products. But here we hope there are investors here in this session. So here we talk about 7-digit budgets at the end of the day. Yeah, so thank you very much for your attention.
Super. Thank you, Clemens. Thanks again. And I do have some contacts working in the medical applications field who talked to me in the past days in the Vienna City Hall who would be interested in this. So I will forward this directly to you, maybe. Next
Great,
up,
thanks.
yeah, we have also someone who was with us in the past days in the Vienna City Hall for the on-site event of the B2B Software Days, Professor Alan Hanbury, full professor of data intelligence at TU Wien.
Okay, good morning, everybody. So I'm Alan Hanbury. I have the pleasure of leading the Data Science Research Unit at the TUV, and that's this bunch of wonderful people. And a lot of what we do has to do with applying artificial intelligence in practice. So, I mean, if you just look at a very broad, abstract view of what artificial intelligence is that covers everything, you take some data, you apply some algorithms to it, and you get an output. When you use artificial intelligence in practice, what people often forget is the most important thing to consider is the context in which you're applying it. Because if you don't consider this, in practice, it tends not to work. So what exactly is this context? And I've broken it down into three most important aspects. The top one being the data. So you have problems of data quality. How can you get around having poor data that you didn't collect properly? What's often underestimated is the amount of manual annotation that's needed to get artificial intelligence algorithm to work properly or well enough. There are also problems with data privacy. So sometimes you can't actually see the data, but you still have to, you're not allowed to see the data, and you still have to do things with it. Another aspect to consider when putting artificial intelligence into practice is that there are going to be people using it. So you want the artificial intelligence to support the people. And so you have to consider the users. And we often work with users who have a lot of expertise, like lawyers or legal experts, medical experts. And they have a lot of implicit knowledge and various expectations about what they want the artificial intelligence system to do for them. They have really strong expectations, and it's very it's very easy to not meet these expectations, and then people are unhappy with the system because it does something that they don't need. And finally, with these sort of people, they generally carry out work tasks. So they don't just use AI because it's fun. They have something that they want to achieve as part of their work processes. So they have some sort of goal that they want to achieve. It could be that there are some requirements for transparency and reproducibility. So especially in, for example, the legal domain, if somebody's used AI to help them with a task and they get some result, if they do the same thing tomorrow or a few days later, they want to get the same result. They don't want to get a different result because then it doesn't make any sense to use AI to help. So you also need to work out exactly how to use the tasks there. So a few examples of projects that we've done. Legal text analysis that we did with the city of Vienna. So essentially taking the Vienna building code and some documents associated with that and converting sentences there into logic statements so that it could then be used for reasoning. We also do a lot of recommender systems. So here's some of our company collaborations in the field of recommender systems. So for example, using dialogue systems instead of classic recommender systems. So getting some chats to do recommendations, fashion recommendations. So you need some sort of diversity in the recommendations. You don't want to keep recommending the same thing. And also fairness and bias in news recommendations. And this all happens under the umbrella of digital humanism, which was introduced by the TUV and has become very popular. So this is how to use technology in accordance with human values and needs. So what we're interested in is projects with companies that have really difficult problems, sort of technical document analysis and search, really complex knowledge-based tasks, transparent recommender systems, or let's say privacy preserving analyses where there are data that need to be analyzed, but that you're not actually allowed to look at. And we have various solutions for this, and I'm happy to discuss with you. Thank you.
Perfect. Thank you very much, Alan. And also thank you for your patience in the past 2 days in the Vienna City Hall. Finally, I'm very thrilled to introduce to you a young researcher who was awarded a spin-off fellowship from our national funding body, FFG, here to talk about her ambition to commercialize her research. So actually science to business. Zara Babai, FFG spin-off fellow at TUV.
Thank you so much. I will share my screen. I hope you can all see my screen. Good morning, everyone. My name is Zahra Babai, and I'm a computer vision researcher and FFG spin-off fellow at TUV. I am also leading the project EVIA, and the FFG project, where we are working on efficient and transparent visual intelligence for autonomous driving and mobility. Imagine you're sitting in an autonomous car traveling at high speed when a child suddenly runs into the street. In that second, AI must detect, understand, and react, and there is zero room for error. This is exactly where we are working on. 5 years ago, I started my PhD research by studying a fascinating structure in our retinal ganglion cells. This is the structure called center surround that actually enables you right now to see the slides. We successfully could translate this biological principle into a novel AI architecture, which enhanced the accuracy and the robustness of the model. And this was just the beginning. The real revelation came 2 years ago when I was sitting in my office and I was looking at the trained neurons or filters of a state-of-the-art vision model that I had just trained. And I found out that the structures, the patterns emerged are very similar to those that I had seen in the retina, in the human vision system. And I was excited. This was the beginning that we started to decode all of these filters, and we could successfully decode all of the filters, almost 99% of the filters of this state-of-the-art model, and we could assign them the exact mathematical formula that is derived from the Gaussian and Gaussian derivatives. And that's exactly how the neuroscientists actually model the vision receptive fields in the mammals and in the humans. And this led to the second breakthrough, which was extreme efficiency. We found out that we don't need the extreme complexity of these models to be able to perform very well. Actually, by replacing 50,000 unknown filters with only 8 mathematically unique filters that all are derived from Gaussians and the derivatives, and like the scalar space theory, we could actually maintain the full performance without reducing the accuracy. And this was just not an incremental improvement, it's a fundamental redesign that we can use and leverage to actually first make the models more efficient and also to peek inside these models to be able to kind of try to decode this black box of these models, because right now we are fully aware what exactly the convolutional layers are. There are some other layers in these models that we are now trying to decode as well. And what exactly this brings us, the implications are transformative. Vision AI applications need to process massive amount of visual data instantly and reliably. Where in autonomous vehicles, security systems, drones, or even Mars rovers, these systems must be very efficient and trustworthy. We are focusing as a first entry on autonomous vehicles as our target market, where the need for reliable and efficient AI is most critical and immediate. And for that, we are actually right now looking as the entry point at the last mile delivery with autonomous delivery robots. We believe that last mile delivery is the ideal real world scenario to deploy and validate our research so far. It's dynamic, it's safety critical, and it's rapidly growing. And at the same time, it's not in the full scale, it's not like autonomous vehicles that are very hard manageable and a scalable environment. And so far, we have received the FFG Spin-off Fellowship Award. We just started less than 2 months ago, and in this period, we have had very good progress. We have already fully finished the teleoperation system for our robots. You can see our robots here is a bit messy, but it's all Harvard hardware labs like that. And you can always come up if you are based in Vienna. You can come to our lab in the CPS group at the Informatic Institute, and we would always be happy to chat and see you just what is the process and what are we working on. And for our robots, we only use camera-only approach. We don't use any LiDAR or expensive sensors because we want them to be scalable. We want them to be cost-effective and be able to do it in a larger scale in the future. And right now we are looking for pilot partners and collaboration opportunities. So if you're involved in logistics, last mile delivery, or if you want to do some automation in the warehouses, like there we can also do some kind of delivery for you. So we would be very happy to hear from you if you are open to do a partner or pilot phase together. You can connect me with my email address here. And also, as I said, you can always come by in person. It's always more fun in person.
Thank you very much, Zara, and also the invitation to speak directly to you face to face. We're through. The time is up. I'm so sorry. We maybe can still show the results of the poll. Yes. And with this, please get in touch with us. We posted the links to the respective universities in the chat. I know this has been very fast-paced. Thank you for sticking with us. And thank you to all the speakers who broke down their work in just 4 minutes in a lightning talk so short. Thank you all. Have all a nice day. I wish you all a nice day, and a servus from Vienna.